Okay, sorry, that was so um, so we were just looking at this, and to summarize, the idea is that a p-value of 0.05, what's its Bayes factor? What's this ratio, the here? And the answer is it depends on assumptions under H1, but if the effect size, if you assume under H1 the effect size are very small, then you get something a small kind of you get something close to the null for the p-values, and so you get a Bayes factor close to 1. If you assume they're a bit bigger, you start to get Bayes factors that are bigger than 1. But if you assume that the effect size are really big, then 0.05 start to become the Bayes factor against the null again. So let's go back to the, if you want to see this actually computed explicitly, is this vignette here. So just take a look at this. So this is just talking about the Selker et al. Bound. And here, what I do is compute a Bayes factor under an explicit alternative that the effect sizes are normally distributed with mean 0 and some variance. So it's just here, that's there, H1. Okay, so under that, and then I just vary that variance just to illustrate the idea. So if the variance is 0, then H1 is actually the same as the null. And then as the variance gets slightly bigger, that's kind of small effect sizes under the alternative. And then when sigma squared gets really big, that's really big effect sizes under the alternative. And for this prior distribution, we can explicitly compute the Bayes factor, because if the effect sizes are normal 0 sigma squared, then we've got a test statistic that's, say, normal theta 1, like a z-score. So under the null, x would be normal 0, 1. So think of this as a z-score. Yeah. So you would get two normal distributions, basically. So your Bayes factor becomes just the ratio of these two normal distributions. And if you plot what the Bayes factor looks like, the black line here, as sigma varies, of course, at the null, sigma equals 0, as we said, the alternative and the null are the same. So this is the extreme where under the alternative, the effect sizes are actually 0, bit of an extreme alternative. That's the one extreme. And then as we effect sizes go up, the Bayes factor at 0.05, this is a p-value of 0.05, at 0.05, the Bayes factor goes up for a while, and then it starts going down again as sigma gets bigger and bigger, because the probability of seeing a p-value of 0.05 under those very, very big effect sizes is actually very small. Essentially, you expect to see p-values much smaller than 0.05, and the probability of seeing something as big as 0.05 is very, very small. So this is what the Bayes factor looks like. And the red line here is the bound from Selker et al. So you can see their bound encompasses all all the range that I've got here. And if you look at 0.01, you can see similar idea. This is p-value of 0.01. Actually, for any given p-value, this kind of behavior is gonna happen. Okay. So I hope that's clear. So what are the main take-homes here? Well, the first one is really, can't emphasize strongly enough that although you may have been told that p of 0.05 is kind of significant, it's never strong evidence against the null to see a p around 0.05, right? The problem is, of course, p less than 0.05 could be p much, much less than 0.05, but p near 0.05 is never strong evidence. And in fact, many statisticians think that the routine use of 0.05 is a problem and causes a lot of false positives. And they argue, well, one paper has just simply argued that everyone should be using a p-value threshold 10 times smaller, which wouldn't solve the problem in every case, but arguably at least it would sometimes constitute strong evidence against the null. And this Bayesian version of the testing here is just some notes on it. It just duplicates that vignette I've just shown you, so you can probably ignore those. Maybe I should remove those. Okay, so that's that for now.